In section 7.3, we're looking at double angle formulae. Now, I like to call these double angle formulae and half angle formulae because often the problem is that people think of them. So if we take the first one, for example, sine of 2a is 2 sine a cos a, and we'll prove that in a moment. But people think of this as, well, this angle here is double this angle here. So I've got to have a theta here, and this thing is a 2 theta. But it also works like this. For example, I'll call it b this time just so it looks different. Sine of b is equal to 2 lots of sine of b over 2 cos b over 2. So the only thing that's important is that the input to the sine and cos functions on this side is half the input to the sine function on this side. If I write this one as 2a, then I've got to write this one as a. If I write this one as b, I've got to write this one as b over 2. Often, as you're first getting used to these, people want there to be a 2 here, and when there's not a 2 here, they think, well, I can't apply this formula, but you can, of course, you can. So often we call this one the half angle formula, this one the double angle formula, and of course halving and doubling just depends where you're starting. So this number here needs to be half of this number here, or this number here needs to be double this number here, or this amount, perhaps I should be saying. So let's go back a step. Let's actually prove where this comes from, and then we'll have another look at the application. So, well, sine of 2a is the same as sine of a plus a, which is sine cos with a plus sign in the middle. Well, if we've got a and a, then these are all a's, aren't they? Sine a, cos a, sine a, cos a. Don't have to worry about which one's an a and which one's a b, because these are both a's in here. So if the number's the same, then that is identically equal to that, which is just 2 sine a cos a. Okay? Similar one for cos. Well, cos of a plus a, or cos of 2a, is going to be cos sine. There's a minus sign in the middle, and again, all of these are a's. So we get cos squared minus sine squared. Now, as you know, we have this formula as well. Sine squared plus cos squared is equal to 1. So I can rearrange this so that 1 minus sine squared is cos squared. Oops. So if I take cos squared in here and I replace it with a 1 minus sine squared, then I get that 1 minus 2 sine squared a is also equal to cos 2a. Okay, so this thing is equal to this thing, which can be rewritten as this thing. And if you do the same trick and you replace sine squared with 1 minus cos squared and you do the rearrangement, then that's where you get the 2 cos squared minus 1 from. Okay, so with the cos 2a formula, there are 3 different versions of it. Oh, the identity, I should say, rather than formula. There are 3 different versions, and they're all helpful. You need to know all of them. You need to have them all at your fingertips and in your head. So there's a bit of memorising to do in this chapter, as you may have guessed already, of lots of different identities. The tan 2a formula, well, that's tan of a plus a, so that is tan a plus tan a, over 1 minus tan a tan a. Now, I don't know about you, I always hate these tan identities here, always seem a real mess, but this is the best that we've got. So 2 tan a, 1 minus tan squared a. So that's our formulae from the book, recovered, right? That's where we get them from. So, how can we use these? Well, first of all, we can use them this way around. When you've got cos squared minus sine squared, you know that it's cos of 2a. So you have to be on the lookout for this in the same way you'd be on the lookout for a difference of 2 squares or an expression that would factorise. When we see this, we need to go, aha, I've got a cos squared minus sine squared. I can turn that into a cos 2a. So that's the same as cos of 100. This one, look, is in the same form as this. So if I double the pi by 6, I get tan of pi by 3. This is sine 70 over sec 70. Well, that doesn't look like any of these 3 things, but if I rearrange it, that is, sec is 1 over sine, so this is 4 sine cos. So 4 sine of 70, cos of 70. And then, well, for my identity to work, I need to have a 2 in there, but we just have to fiddle around a little bit. So 4 is 2 times 2, right? So 2 sine 70 cos 70 is sine of 140, and then we've still got the 2 left at the front. So the first thing we can do is we can just use them as identities, and when we're simplifying our identities, we need to be ready to spot them and use them. What else can we do with them? Well, to be honest, we can have a look at example 8 and 9, but there are so many different ways of applying these in the same way as there are with all the other trig identities, that the examples here, 8 and 9, are just they're examples. There is a sort of, well, this is one possible application. A lot of the time in the book, the examples they give you are, okay, these are the kinds of questions you're going to meet. But in this case, it's just, here are 2 possible things we can ask you to do. You'll see lots of other different example applications by the time you finish the exercise, right? So we can't do a huge amount. I'll run through those in a second, but what I'd say is that what to look out for is when you've got a sine times a cos, and they've both got the same input, you're thinking of turning it into sine 2a, right? You're remembering this identity. When you've got cos squareds and sine squareds, or particularly cos squareds minus sine squareds, then you're thinking of that they will turn into cos 2a as well. So far, when you see a cos squared, you know that you can kind of convert that into 1 minus sine squared. Now when you see a cos squared, you know you can convert that into cos 2a, and that particularly is going to be useful when we come to integration, okay? So let's just have a quick look at example 8 and 9, just in case they're bothering you, but again, it's not really as though this is the application for them. It's just, here are some examples of things that we can do. So if we have these things here, we go on to eliminate theta. Well, if I've got sine theta, this one is already written in terms of sine theta, and I've got cos 2 theta, so it's difficult to see how I can get rid of the theta. And the trick is that cos 2 theta can be written just in terms of sine squared. So I'll change cos 2 theta into the version that is sine squared, and then I can eliminate by substituting in with the sine squared instead of, we can't find theta on its own and then substitute in later. So that's how that little trick worked. The reason we would have spotted it is because cos 2 theta can be written as something in terms of sine squared, and x can be written as something in terms of sine, okay? Now, I wouldn't panic if you wouldn't have thought of doing that for yourself. Of course you wouldn't at this stage. When you've done the next chapter, I think it's the next chapter, the parametrics chapter, we see this sort of trick a lot. So this is really a question taken out of chapter 8. Let me just double check. Yeah, chapter 8 is parametric equations. This is really a trick taken out of the parametric equations chapter, and they've put it here just to give us an example of how the double angle formulae might work for us. And then we've got another one of these examples. They tell us the exact value of cos. We want to find the exact value of sine 2 theta, sine 2x rather, sorry. Well, if I can find the exact value of cos, I can find the exact value of sine, and then I can write sine 2x in terms of sine and cos. So we can do that one that way, similar to what we saw in section 7.2. So everything that we've learned so far, we can apply to the same sorts of things that we've done previously. We can solve trig equations, we can simplify trig identities, and we can fold it into all the other maths that we've seen. Trig got difficult when we started introducing identities, didn't it, in the year 1 blue book, and now we've got so many more identities from chapter 6 and from chapter 7. It's just going to make those identities, the simplifying identities questions, pretty nasty and pretty complicated. But the technique for solving them is still the same, it hasn't changed. Look at the question, think of everything you can do, think of what tricks you can apply, and then work from there. So good luck with it. That's the end of 7.3, 7.4 in the next video.